Okay, y'all, I know this wasn't the plan, but you're going to have to watch this video to get the last video review on forces. These are the three papers that you're going to need. The quiz on free body diagrams and net force equations. It was a one-page quiz. I think there were maybe 3 versions of this quiz. It was dated November the 4th. Also, you're going to need the quiz on 2D forces on inclined planes. I think maybe this paper had been front to back, dated the 13th of November. And then finally the big forces test. It was about 2 pages front and back, dated the 18th of November. So find those 3 papers, get them in order before you proceed with this video. The key to 2D forces is to be able to write net force equations. You mastered this equation, force equals mass times acceleration. But in truth, it's the net forces equals mass times acceleration. Writing a good net force equation depends on the free body diagram. It's a translation from the diagram to an equation. As you recall, these dealt with having something at an angle, either a push or a pull at an angle. We have to identify all of the forces involved and label them on the free body diagram. We can have the weight pushing down and the normal force pushing back up. We can have friction going against motion, and then we can have the applied force. If the applied force is at an angle, then we have to split it into its horizontal and vertical components, and then include those in the net force equations. Let's write the 2 net force equations for this example, the horizontal, then the vertical. In the horizontal, we have the force of friction, and we have the x component of the applied force. If there's motion in the horizontal, we set this equation equal to ma. Now, in order to put in the value for the force of friction, it's probably given, and it'll probably be a negative number because it's pointing to the left and in the opposite direction of the motion. To get f of x, remember we'll have to do the applied force times the cosine of the angle. Since this is to the right, that'll probably be a positive value. Now, when there's motion, we set the equation equal to mass times acceleration. Typically for these, everything is given but one element, and then we use this net force equation to solve for the one thing that we don't have. If we look at everything in the vertical, we can add those together into a net force equation. In this case, we've got the normal force, the force of weight, and the vertical component of that applied force. Now, if there's vertical motion, we set it equal to ma. Since we've never dealt with any hopping boxes, we'll assume that there is no motion in the vertical, and so we set it equal to 0. Everything horizontal goes in that horizontal equation. Everything vertical goes in this vertical equation. That's why we call it the sum of the net forces, and we use a sigma, because it is all of the forces added together. Now, if there was no friction, then that would not have been part of that equation. If there was no motion, that would have been set equal to 0. That's what dictates what goes into these net force equations. That's why I never could just give you the equations. It depends on the situation. It's all about you translating what's going on in this diagram into these net force equations. Alrighty, let's look at this free body diagram and net force equation quiz that you took. This may not be the exact question you have, but the idea is about the same. It starts with a free body diagram. In this case, it was being pulled to the right, and the rope made an angle. So to do the net force equations of everything vertical, it involved the vertical component of that applied force, F cosine theta, and there was motion to the right because it said so in the question, so we put it equal to ma. For the vertical, we have normal force, force of weight, and this vertical component of the applied force. And there's no vertical motion, so it's set equal to 0. Now in these cases I didn't have you put any numbers in, but when we did go put numbers in, weight would have been a negative number, and Fy would have been F sine theta. That would have been positive, just like the F cosine theta would have been positive, because the supplied force was positive to the right and positive up. For the second one here, we show something being pushed to the left. The biggest difference is going to be in the sign of that applied force. So the sum of the horizontal forces is the x component of the applied force, and that's going left, that's negative, and equal to ma because there's motion. For the y, we've got normal force, force of weight, and then the y component of that applied force is down, which when we put numbers in is going to be a negative direction. No motion vertically, so we set it equal to 0. The rest of this quiz was about hanging, and even though that is part of 2D forces, it's not on the final. So let's just not revisit that horror story right now. Let's go on to the next paper. The next paper is the quiz on 2D forces and inclined planes. A lot of similarities with the boxes that we're pulling and pushing on a flat surface, only now instead of talking about x and y, we're going to talk about parallel and perpendicular. The key elements here are the free body diagram. To draw the free body diagram, we need to know important information like the fact that it's frictionless, and we need to know if it's moving down or not, if it's at rest or if it's sliding down, because that will affect our net force equations. So in this one, we've got a box that's sliding down a frictionless surface. Straight down is the force of weight. Not straight up, but perpendicular to the surface, we have the normal force. Extending down at that angle is the perpendicular component of weight, and in line with the ramp itself is the parallel component of the weight. As we do with things at angles, we resolve it. In this case, we resolve into perpendicular and parallel components of weight. W cosine theta for perpendicular, W sine theta for parallel. To write the net force equation for perpendicular, we're going to list everything in this plane, perpendicular to the ramp. That's going to be the normal force and the perpendicular component of weight. And since that's down, we know that the value going in is going to be a negative value. And since there's no motion, it's set equal to 0. So essentially, we discover that the normal force is equal but opposite to the perpendicular component of weight. In the in the parallel component of forces, it's everything parallel to the ramp itself in this plane. So we've got the parallel component of weight, and we do have motion, it's equal to ma, but there's no friction. So from the resolved forces, we put in our value for W parallel. We have a value for the mass of the box it's sliding down, and we're trying to solve for acceleration, and that's just done algebraically. Okay, the problem below that, same page. It depends on this question as to how the free body diagram and the net force equations are going to go. In this case, we have something at rest, not sliding, and there's a coefficient of friction mentioned, so we know that it is not frictionless. There must be some friction. As always, we want to resolve our perpendicular and parallel components right off the bat because we know we're going to need those numbers. The net force in the perpendicular is going to be everything in this plane right here. So that's the normal force and the perpendicular component of weight. One going up, one going down. Set equal to 0 because there's no motion perpendicular to the incline. For the net force of the parallel, it's going to be everything parallel to the ramp itself. That's going to be friction and the parallel component of the weight. And this time, because it's at rest, we set it equal to 0. So you notice that neither one of those equations is set equal to ma, because there is no a. It's at rest. And then in this particular example, you had to solve for the coefficient of friction. We will not be doing that on the final exam. Next page, let's run through these. It's a lot of concept questions. Number 11, make sure that you know the definition of weight is the force of gravity acting on a mass. And make sure you know how to calculate that. Weight is equal to mass times gravity at negative 10 meters per second squared. Know a couple things about friction. as in it's found at the contact surface, it runs parallel to the surface, and it acts in the direction opposite of motion. Number 13 and 14 are related, as you'll recall, and this goes back to writing net force equations. When something is at rest, the net force equation is equal to 0. If the net force equation is equal to 0, it's because it's at rest. They're saying the same thing, but in the opposite direction. Number 16 refers to a free body diagram, and it's talking about the perpendicular components. Make sure that you realize that on these incline problems, that the normal force is equal but opposite to the perpendicular component of weight. And then at the very bottom of that page, all we're going to worry about is number 20 here. It refers back to a free body diagram, and it's asking about the normal force, which is going to be a perpendicular component. So you need to know how the net force equation would work out. Normal force one direction, perpendicular component of weight the other direction, equal to 0 because there's no motion. And we know that when we resolve the perpendicular component, that is weight times the cosine of the angle, and that's going to be equal and opposite to the normal force. Okay, we're on the home stretch. You need your big test on forces. Some of this is repeat from what we talked about on Friday with the 1D forces and Newton's laws quiz, but let's go through the whole thing again. Okay, page 1, Newton's laws. Make sure that you know what is the law of inertia and what is not the law of inertia. In this case, something will continue to move unless an outside force acts on it. Something will stay in a straight line until a force acts on it to turn its direction. Something will not move and stay at rest unless a force acts on it, which is also what D says. So it's all of the above. Make sure that you understand about the equation F equals ma and the relationships found there. That mass and acceleration have an indirect relationship to each other, that if one goes up, the other has to go down in order for it to be equal to the same force. That force is directly related to mass, and force is also directly related to acceleration. Remember, the derived unit of Newton is a kilogram meter per second squared, slightly different than the derived unit for a joule. Make sure you can tell the two apart. Continuing on, we've addressed this question before. Concept is, if the net forces are 0, the object is not accelerating. So what are the situations where something is not accelerating? It's either at rest or at constant velocity. Number 9, because of the gravity on Earth, all objects, regardless of their size, shape, mass, if you neglect air resistance, they all fall at the same rate of negative 10 meters per second squared. All right, number 10. Number 10 is talking about, okay, so this is the net forces equals ma. In this case, it's a 1D problem, so the net forces are the 450 force one direction and the 250 force direction in the other direction from friction. So if we take the difference between those and set it equal to ma, we can solve for a. Number 11. Looks like it's also F equals ma. So you're taking something and accelerating it, I guess, horizontally at 2 meters per second squared, and it has a mass. How much force would it take to do that? So just plug in and solve for F. Next page, number 13, this is the elevator question. What I need you to know for the final is that if it's accelerating up, your weight appears to increase, and if it's accelerating down, your weight appears to decrease, and if it is not accelerating because it's at a constant velocity, or if it's at rest, there is no change in the apparent weight. All right, you'll notice we just skipped some stuff. Now we're down to question 18, which is a similar question that we've already had on a previous quiz. Just know what there is to know about friction, please. At the bottom of that page, that little set of problems 23, 24, 25 is about net force equations in 2D. So we have a wagon. The wagon has weight down, it has a normal force up. It does not specify frictionless, so it has friction in the opposite direction of the applied force. And the applied force is at an angle. Since it's at an angle, we will resolve it into its x and y components. As always, f cosine theta for x, f sine theta for y. And then we just need the net force equation. So it starts with the net force in the horizontal. Everything horizontal here is the friction and the horizontal component of the applied force. So that's what gets listed. Since the wagon is being pulled, and we know something about wagons, like, they move when you pull them, we assume there's motion. We'll set it equal to ma. For f of x, substitute in the f cosine theta. Friction in the opposite direction. There we go. It's a negative number. Put in the mass. Solve for a. You should be able to rearrange mathematically to solve for a. Then for the sum of the forces in the y, we need normal force, force of weight, and then also the y component of the applied force is in that same plane. So we have three things: the y component, normal force, force of weight. The y component is f sine theta. We don't have a number for the normal force. We do have the weight based on the mass, because mass times gravity gives us the weight, and it's negative because it's going down. And there's no vertical motion, so we set it equal to 0. Then we just go through the math and solve for normal force. Again, we're skipping the hanging question. Hooray! Okay, we're at the end. Number 28. What, I feel like we just talked about that. Oh, okay. So now we've got something on an inclined plane of 30 degrees. And we could draw the free body diagram for that. But this is asking about normal force. And our experience with normal force tells us that, let's see, here's the little thing, that the perpendicular component of weight, remember that's weight straight down, is going to be equal and opposite to the normal force, so we just showed it mathematically here. That the normal force is equal to the perpendicular component in the opposite direction, which would be w cosine theta, and then you get the answer. Okay, last free body diagram here shows a rock on a frictionless ramp, and it is sliding down, so it's going to go, which means that one of our equations, the parallel equation, will be set equal to ma. Okay, it has weight. Weight has components, perpendicular and parallel. There will be a normal force in line with the perpendicular component, right? No friction. Okay, weight of the rock is going to be mass times gravity. Then the net force in the perpendicular will include, as always, normal force and perpendicular component equal to 0 because there's no perpendicular motion. We put in f cosine theta for the weight and get an answer. For the parallel, everything parallel includes this parallel component of weight, and that's it. And then it's equal to ma. We put in weight times sine of theta for the parallel component of weight, and then solve for a. Okay, if you can do these, then you can answer the questions on the final exam. We've painstakingly gone through everything there is to go through. It's your job now to go back and study with intent and come in with a clear head on your day to take the final. Good luck, everybody.